Hello everyone, welcome to this video. This is lecture number 7 and part 2 of the special function. Already part 1, that is the Bessel function, already discussed. In this lecture we want to discuss about the Legendre function. Okay, so from previous lecture you can watch this portion already covered, that is the theory of second order differential homogeneous differential equation, inhomogeneous differential equation, that is green function, and within this special function already we Bessel differential equation whose recurring, orthogonality and series expansion are covered, and in this lecture we want to cover up the Legendre differential equation whose recurrence, orthogonality relation and series expansion. So let's start. This is the Legendre differential equation. This is very well known or useful differential equation in physics related problem. If you want to find out the singularity of this equation, you can check that at x equal to 0 both are the finite. So you can say this is a ordinary point at x equal to 0. When you want to find out at x equal to plus 1 or minus 1, you will be get this or infinity, but if you products are finite, so this will be get regular singularity. Also in case of x tend to infinity, you will be can check this will be regular singularity. So you can see there these are the regular singularity, and you know that the second order differential equation can be solved in the series solution, that is Frobenius method solution, only when the point is ordinary point or regular singular point. So you can solve this equation by series solution. So take this series as a y equal to ar x to the power k minus r. This is notation to get the Legendre function. That's why we take this type of formation. Okay, then for first order derivative, second order derivative, put these values in this differential equation and then compare the coefficient x to the power k. Will be get there is no x to the power k, because if you want to find out the coefficient x to the power k, you need to put here r equals to r minus 2. This is not possible because r start from 0. So in this part we will so in this part we will does not get any term. Here we will get only this term. Okay, so that's why this is written as 0 and this term will be 0, and since a0 is not equal to 0, you will be get the value of k like k equals to 1 and k equals to minus n minus 1. Now if you want to compare the coefficient of the k minus 1, similarly this term will be 0, and from there you can see if you can take a1 equals to 0. A0 cannot be 0, but A1 can be 0. If you take A1 equals to 0, then this is the as the solution. There is no problem to take A1 equals to 0. Now if we compare the coefficient of x to the power k minus r, then from first term you will be get this term, from second term you will be this term, then after that you will be get this relation between the two coefficient between a r minus 2 to a r. Okay, this is known as the recurrence relation, because when you know this term, this will upgraded to u, and after a r you will get a r plus 2 and so on. In case we take the k equals to n, that is we get these two solution, that is k equals to n and minus n minus 1. So at first we take the solution x equal to n, then this recurrence relation where put this k equals to n, here put the k equals to n, we get this recurrence relation, and after that you put the value of r, that is 2 4 and so on, you will get the generalized coefficient like that, and a3 a4 a5 equals to 0, because a1 0, and that's it, the odd term will be 0. Solution for y equals to, we will be get this equation. So you can solve write down in the, since this is only even function, so you write this here and put this ar value, you will be get this expression, and after that if a0 equals to this, then the solution become Legendre polynomial like Pn, and this is the first kind solution, and put the value of this a0, you will be get this type of expression, just follow up, then just put the value n value, you will be get the different Legendre polynomial p0x p1x p2x p3x and so on. Okay, and if you take the another value of k, you will be get this expression, and this is the general coefficient, and after that if your solution will be like that, and this is taken as the second kind legendary polynomial. Take the a0 equal to like that, and this is a non-terminating series. Okay, and their combination is a general solution of this legendary equation. Now comes into the generating function of this legendary polynomial. Take this is a generating function. If you can prove that this will be matches with this function, the summation function will be matches of this function if you expand this. Okay. Now you want to, if we wants to prove this relation, that is the g xt will be like that. Now if you put x placed by minus x and t placed by minus t, this both are minus, so this will be in the same, and this is the minus whole square, this begins the same, but here you will get this relation, and this can be represented by this. So if you put here, and if you compare the coefficient of t to the power n, you will get this relation obtained. Next, these are the various recurrent relation you need to prove. For that you can follow up this process. Here the generating function take with respect to x derivative, and this portion break into two part, and this is nothing but the this generating function, and then compare these two. You will compare the coefficient to the power n plus 1, you will get this relation. Again this generating function partially derivative with respect to t, and after that if you compare to the power n, you will get this type of relation. Okay, then differentiate above this with respect to x of the above relation, and just follow up this process written here, just follow up this process, you will be get this relation. Okay, so this recurrence relation can be obtained by adding, subtracting, and so on by different process. Just go through this process, you will be get these relations. Okay, and so on, all relation can be obtained from this mathematics. Okay, and there is another one. Now comes into Rodzinger's formula for the legendary formula. This is the formula. You by this formula you can find out also the legendary function. Suppose you put the n equals to 0, you will be get 1. We already obtained this p0x is 1, because from when we define the legendary polynomial in this equation, here you can see here this is p0x is 1, p1x is s, p2x is like that. This all legendary function can be obtained by this Longer's formula. By this Longer's formula you can obtain this relation. Okay, just put this value, you will be get. And this is the property of the orthogonality of this legendary function delta mn. This is a direct delta function. You know when these are the same, you will be get 1, otherwise this will be 0. So when these are the same, here you written as these are the same, that's why this one, no, this is a special function. Okay, and if you want to draw the curve, p0x is 1, so this is constant, p1x is x, so this is straight line, p2x is like this parabolic curve, p1x sorry, this is p2x, I think this is, we need to correct this one, that is this was p1x, this is p2x, p2x, this is p3x, this is p4x. Okay, this is correct. Okay, so that's it. p0 p0x, p1x, p2x, p3x like that, this is p3x, p4x like that, p5x again like, and so on. Okay, this is the legendary series. This f of x defined as this legendary function where n is like that. This is the legendary series, and this is various application legendary function, mainly the solution of the Laplace equation in the spherical polar coordinate system, potential and field problem in the electrostatic, earth gravitational field, where actually we use the spherical polar coordinate system, we got this legendary function, and we can write down the legendary solution. Okay, and this is the question asked in the previous year, you can solve this question. Okay, take the screenshot and solve this question. So that's it. Thank you.